Good morning, everyone. I have the pleasure to present the work which we were doing with my team in collaboration with the colleagues from GNSS company, Jandosh and Pavel Václavovich. So this presentation actually goes to a shorter time scale, basically using real-time GNSS data for storm monitoring. So here I'm using storm nowcasting, and I think it's really important that I define this. The World Meteorologic Organization defines nowcasting as detailed description of current weather and forecast 0 to 6 hours ahead. So here we are talking really for a very short range forecasting. The phenomena which are of interest, of course, are a large number, but on this talk I will concentrate on convective storms, and of course, precipitation is often associated with those convective storms. Why it's important to do nowcasting? Actually, all of you have traveled to come here, and aviation on Sunday was really in a big trouble because there were a lot of storms around. And you know, for this short period, you really need to be able to give exact location of those storms so that the flights really go around them. So this is really transportation is the main impact, but also for agriculture, for example, when you have hail and then all the production is destroyed, it's not really very nice. So this is really large economic losses, sometimes not human. But how is this done actually by meteorologists? Basically, the standard observation which is used or the technique is weather radars. With weather radars, actually, what we do is actually we track the clouds. You track the GPS satellite, so basically the same story. With radar, we detect the cloud, and then we track its movement, and then after long tracking or enough time tracking, then we can extrapolate and predict. So basically, it's the same like you have orbits, and then you have prediction for those orbits. So this technique is widely used everywhere. However, in the last 10 years, there are techniques which have been proposed and which can really help to improve tracking those clouds. And those techniques are based on in-situ observation, very short range numerical weather prediction, but also very much in the last years on machine learning as well. So I'm going to tell you today how we integrated GNSS derived water vapor into tracking the clouds. So in Bulgaria, you see a map here. So basically, Bulgaria has really quite a diverse topography. So we have plenty of mountains. But our agricultural production area here in this green area where we produce fruit, and here a lot of wheat production. So together with the Health Suppression Agency in Bulgaria, we were able to install 12 GNSS stations which are only used for tropospheric monitoring. Those stations provide real-time RINEX files, and then our colleagues from the GNSS company process this in real time, deriving the ZTVs. For the demonstrator, we also did reprocessing with near real-time data to validate the real-time products. And then, using the work model, we compute the integrated water vapor from GNSS. Then this data is posted on a publicly accessible geoportal. We also did analysis, time series analysis to derive integrated water vapor, and I'm going to tell you more about the storm threshold which we have on the demonstrator here on the web portal. So, one word or one slide about validation. There is a poster which Jandosh is first author and his team, you can check it out, but basically for this product we have seen that the real-time ZTD bias is in the range of 3.85 with the standard deviation 6.5. Here you see the bias on monthly average and on daily basis for those 5 months. And here is the standard deviation also for one station. But this is similar, I can assure you, this is similar for the other stations. I said we did the time series analysis. For this we used the longest operated GNSS station in Bulgaria, which is the IGS station Sophie, some of you may know it. So for this station actually we used meteorological observations to derive the days with thunderstorms and without. And then for those days we used the maximum integrated water vapor measure. And then you see those two plots. Actually, with the red one is the days where you have very high values, and those are associated with thunderstorms. There is, however, a second peak with thunderstorms, which actually coincides with the peak of the days, the blue one, when there were no storms. So this actually graph I really want to highlight here that actually because of this you could not really predict the thunderstorms with GNSS alone. So if you really try to do this, you're really in those areas where you have overlaps between the integrated water vapor values. For this reason actually we use meteorologic observation from the radio sound and computed 8 instability indices. So the message here is water vapor is one of the factors which really contribute to severe weather. It's not the only one, however. And then we computed the classification functions based on these instability indices, which is this one. You see it here for May. And then we computed the probability of detection of thunderstorm, the light blue, and the false alarm rate. So if you could not read here, but it's around 80% probability of detection and false alarm in the range of 30%. Then to these indices we added integrated water vapor, and we computed the second classification function using integrated water vapor and instability indices. And then the results were really very promising because we could really increase the probability of detection of thunderstorms, and what is even more important, we decreased the false alarm ratio. So these results actually were quite promising, and they are published in a paper. You can check there for details. So it is for May, June, it's quite consistent result. This demonstrator actually was developed as a part of the ESA-funded project, and we actually did also one case study with the hailstorm on 28th of August. So basically what you see here, we have a threshold which is in red color, so this one. And what you see after 26th of August, there was high values of integrated water vapor, but severe weather did not happen all the time. It just happened towards the end of this period, where we had the orange code for 29th of August. And however, we know from our analysis that on 28th of August was more severe convection, and then from the radar data we can derive that the average altitude of the clouds went to 14 kilometers versus 8 kilometers on the next day, which is actually something we have also shown here on this graph, how the integrated water vapor increase was happening before the cloud development, so we track this gradient. We also looked at the gradients. You know, topography is really main factor here, but I can point here, for example, here the gradients point to the same direction, but have a look here where we have this valley, and they're totally in different directions. So there is convergence, and this is really interesting, but very difficult to explain. You really have to look at the weather situation, and the maps are here. So this is really the beginning of this analysis on the case study, and we see, for example, on the next day where there was a cold front passage, the gradients were very strong. So, but still, you know, you see some divergence here in this region. All right, so when the project finished, actually, one day afterwards, we had the severe weather coming, so, we were very fortunate, or, misfortunate, to look at this severe weather. On 1st of September, there was yellow quota issued for thunderstorm and rain for Bulgaria. For the next day, it went orange region. There were widespread thunderstorms. You see those are color-coded, but there are very few areas without thunderstorm. Rain, very intense precipitation here, and the result was really, everything underwater. We've seen those pictures everywhere. So we had the demonstrator online, and then we looked at it. Basically, those are the stations, and here for each station you have a symbol with orange when it's above the criteria, and with the sun when it's below. So this is the detailed analysis, which is actually with water vapor, and you see that the orange is the real-time water vapor, which goes really high above this threshold which we defined. Here are the classification function. Actually, this classification function was computed on real time, and then on real time, actually, we had to adjust the y-axis because it was really such a high values. We were not prepared for such a high values of this classification function. So the classification function based only on instability indices is this constant line, because we only have those observations at 12 UTC, while adding integrated water vapor, you see over this day we have a much higher variability introduced through water vapor. One minor thing which I want to point out, that at certain point with the storm passing by, actually one of the GNSS station was actually stopped working. So severe weather affected also GNSS infrastructure on ground, and we could really see this in real time again. So I'm close to finishing. I presented to you a storm nowcasting demonstrator which we developed for Bulgaria. I have to say here that this demonstrator would have been impossible without the real-time products provided by this community. So I'm very, very happy, and I would like to thank everybody who really contributed to this and continues to contribute to real-time orbit and clocks, because they can be used and they are useful for monitoring severe weather, and hopefully, we will continue on this direction with more centers. So the team, Jan Dorsha, Pavel Vaclavovic, and my colleagues from the National Institute of Meteorology and Hydrology, Anastasia Stoicheva, and from the Health Suppression Agency, Svetlana Dimitrova, and the PhD student who did most of the work. All right. So thank you very much.